I've been busy building up this homebrew 8-bit CPU here. Recently I've added a liquid crystal display, so the CPU has a mechanism to show output to the user, and it can do some first cool things like computing Fibonacci numbers. However, since the CPU is still fairly simple, it executes instructions exactly in the order they are in the program. An important step forward towards making the CPU out of order is to allow functional units like the LCD over here to finish instructions and write back results into registers on their own. In a sense, the CPU, especially the instruction front end and the decoder, must be able to kick off instructions and then go and do other work in the program and let the instructions complete independently. This is generally called a fire and forget execution strategy. In this episode, we'll start tackling the first half of out-of-order execution, which is allowing functional units to write back results into the register file out of order whenever they are done. And coincidentally, writing to the LCD is already out of order. When the CPU hits an LCD write, it sends it to the LCD unit, but then continues in the program while the LCD unit is still busy executing that write. Reading from the LCD, on the other hand, is not out of order at the moment. The CPU needs to stall and wait until the LCD unit has the read result ready, which it then can take and write into the destination register. Today, we'll make the LCD reads out of order. The CPU should be able to continue executing the program after reads while the read is still in progress. And when the read is done, the LCD unit should be able to write the result back into the register file all on its own. This is how my CPU currently looks like. It has a bunch of functional units that are responsible for executing instructions. This includes moving values between registers, performing arithmetic and logic operations, jumping and branching to other parts of the program, and interacting with the liquid crystal display. Each of these units has a tri-state buffer that allows it to drive its result onto a common result bus, the exception being the branch unit, which never produces any results, so it doesn't have such a buffer. This common result bus is connected to the register file's write data input, allowing the CPU to write the result into the register. Each unit has a valid input, which enables the output buffer, or in the case of the branch unit, enables it to jump around in the program. These inputs are connected to a demultiplexer, which takes a 2-bit functional unit ID and activates one of 4 output lines. This forms a bus that lets us issue instructions to the functional units and ensures that there's only ever one functional unit enabled and driving a result onto the result bus. The instruction decoder looks at the current instruction, decides which functional unit ID should execute it, and lets the demultiplexer activate that functional unit. The decoder also sets the register file's write address to the destination register specified in the instruction, and it sets the write enable according to whether the instruction writes a result or not. And since the LCD unit takes multiple cycles to execute a command, it has a ready output, which it uses to provide back pressure towards the decoder. The decoder uses a multiplexer to pick the ready signal coming back from the selected unit in order to stall the CPU when the unit is not ready. At the moment, only the LCD provides back pressure. All other multiplexer inputs are set to true, indicating that the rest of the units are always ready. Note that in the actual hardware, the valid and ready signals are active low, and these multiplexer inputs are therefore tied low. As a first step towards out-of-order execution, we want to allow functional units to write back results into the register file out of order. This is mainly interesting for the LCD unit at the moment, since it takes multiple clock cycles to finish an instruction. To write back its result independently, the LCD unit must remember into which register it has to write the result once it becomes available. So we need to store this information in some kind of register or latch. Let me indicate this with this vertical bar here, which is commonly used in circuit diagrams to depict pipeline registers or latches. In our actual hardware, the LCD unit already has a latch that holds some information about the command being executed, and we can very likely reuse that and store some additional information in there. Once a read finishes, the LCD must be able to set the register file's write address and write enable inputs to control into which register the result is written. And we'll want to do this through another tri-state buffer, which will drive this metadata onto the result bus alongside the result data. This also means that we have to remove the direct connection between the decoder and the register file and instead use a tri-state buffer. This allows us to decide who gets to drive metadata onto the result bus in a similar fashion as we decide who gets to drive a result. With this setup, we now have multiple parts of the CPU that may want to take control of the result bus and write the result into the register file, which means we need an arbiter that decides who gets access to the result bus in case multiple units want to do so at the same time. And we'll have to add a valid ready handshake to the functional units on the result bus side, since units may request bus access through the valid port, but then get back pressure from the bus through the ready port in case they don't get bus access and have to stall. And then, instead of enabling the tri-state buffers inside the units based on the valid inputs on the issue bus side, we'll only enable these buffers when we're given access to the result bus and get a ready back from the arbiter on the result bus side. This also means that even simple functional units like the move unit or the ALU can now stall because they didn't get result bus access. So we need ready signals on the issue side for those units too, providing back pressure to the decoder and stalling the CPU if necessary. And I think with this we should be able to have the LCD unit be the first part of the CPU that writes its results back out of order. And this arrangement of issue bus, functional units, and result bus is starting to look like a nicely modular execution pipeline architecture for a CPU. The Fibonacci sequence program I'm currently running on the CPU is a little bit too complicated to start messing around with out-of-order execution. Let's go write a simpler test program that just does a few reads and writes on the LCD and tests for a few of the interesting corner cases that we will need to handle. First, let's clear the registers as per usual. Let me also initialize the display at the beginning here, such that that command can run in parallel while we clear the registers. And then 4 cycles later, when that initial write is done, let me move the display cursor to address 10, such that we have a known value that we can read back from the LCD. Once we're done with all this initialization, let's read that cursor position, the position 10, back from the LCD. And since we'll have out-of-order write-back of the LCD results, the CPU should be able to just continue on after this read command and execute other commands. So let me add a few just to keep the CPU busy with a few ALU instructions. And after a few cycles, when we know the read is done, let's move the read result from register R0 into register R1. What I expect to happen in the background is when we do the LCD command read, the LCD unit becomes busy and the result in R0 basically becomes pending. And the next 4 instructions only operate on register R1, they ignore R0, so there's no data dependency hazard. And then after 4 cycles, I expect the LCD unit to write the result back into register R0. And I expect that command read to return the position of the cursor, which is at index 10. This means that the move right after will read register R0 as the value 10 and copy that into R1, such that both R0 and R1 contain the value 10. But let's now try a trickier case. Let's try to provoke a read after write hazard. Let's again read the cursor position from the LCD. And immediately after, let's use the result of that read and copy it into a different register. And what I would want to happen in the CPU is when we do this command read, the register R2, the destination register, becomes pending, the LCD unit becomes busy. But since the next instruction uses that result, there's a read after write hazard, and the CPU should stall and wait until the LCD result becomes available. So if the CPU handles this hazard properly, I would want to see the LCD unit write back its result here just before the move unit before continuing. But if the CPU does not handle this hazard correctly, I expect this move to be executed immediately after starting the command read. Basically, it would just read whatever is currently in the register R2 and move that into R3 without waiting for R2 to be updated with the result. So let me add a few knobs here to give the LCD enough time to write back its result in case we don't handle the hazard. And after these knobs, I expect register R2 to contain the value 10, the result of the LCD read. And depending on whether the move executed too early before the result was available, I either expect R3 to be the value 10 when the hazard was handled correctly, or 0 if the hazard wasn't handled properly. The other issue we can run into with this out-of-order execution is a write after write hazard. This one is similar. We execute an LCD read, but then we immediately overwrite the result of that read in the next instruction. So in the background, I expect the LCD unit to become busy at the read and the register R4 becomes pending. And since the next instruction writes to the same register R4, there's a write after write hazard. And if our CPU handles this hazard properly, it should stall and only execute the load immediate once the LCD command read is done. However, if the CPU does not handle this hazard properly, the load immediate would execute immediately after the command read while the command read is still ongoing. And so this value 16 would be stored in register R4 while the LCD is still doing its thing. And if we add a few knobs to wait for the LCD, I would expect the LCD unit to eventually write back the read result, the value 10, into register R4 once it becomes available. After these knobs, to make the result a bit more obvious, let me copy the value from R4 into R5. And at the end of these instructions, I expect register R4 and R5 to contain the value of 16 if the hazard was handled correctly, and the load immediate into R4 was appropriately delayed until the LCD command read was done. Or I expect R4 and R5 to contain the value 10 if the load immediate loaded the value 16 into register R4 too early and the LCD command read was still ongoing in the background and it ended up overriding that value 16 in the register file with the result 10. So this should give us a good test of the out-of-order write-back capabilities of the CPU, and it should trigger the two common hazards that can occur when you have such functionality. Let me assemble this and then let's see how this runs on the CPU at the moment. To make it a bit easier to follow along and see when the CPU is stalled, let me add a yellow stall LED to the decoder connected to the program counter enable signal, which the decoder uses to disable the program counter in the case the CPU needs to stall and kind of freeze in place until a computation is done. Let me run ahead to the first LCD write in our new program. And these are already out of order because the CPU doesn't need the result. There is no result coming back from a write. And so the decoder selects the LCD functional unit to execute the instruction, but the stall LED remains off, which means the CPU will just continue with the program while the LCD does its work. And then running ahead a little bit, this is the first LCD read operation, and this is in order. The CPU has to wait for the result to come back from the LCD in order to be able to store it back into the register file. So this time the stall LED is on because the LCD unit provides back pressure to the decoder and the rest of the CPU because it knows that the CPU needs the result, so it indicates to the CPU that it needs to wait until the operation is complete. And if I step forward a few cycles until the LCD unit indicates that the result is ready, you can see that at that point the stall LED goes off, which means the CPU is now unstalled and will continue in the program, and the data that comes back from the LCD unit is going to get written back into the register file. Let me run this to completion and then let's check if the program worked. We expect register R0 and R1 to contain the value 10. That looks good. We expect register R2, R3 to contain the value 10. That also looks good. And register R4 and R5 should contain the value 16, which is also the case. Pretty good. So no surprise there, because we stall whenever we read from the LCD, none of the hazards that we're testing for in this test program can actually happen, so we get the correct response in the registers that we would expect. Instead of stalling the CPU whenever we do an LCD read, let's just throw the read at the LCD functional unit and continue in the program the same as we do with LCD writes. This is actually pretty straightforward. We have a ready signal here coming from the LCD functional unit going into the decoder, which provides feedback to the decoder if it needs to stall or not. And this ready signal is coming from this multiplexer chip here. And depending on whether we do a read or a write, we pick one of the signals in the functional unit to determine whether we can continue or we need to stall. For writes, we've just been using the busy signal of the LCD to provide feedback, so whenever the LCD is not busy, it would report being ready to the rest of the CPU and it would just accept the next write. And only if there was an operation already in progress would the LCD unit report back that it wasn't ready. And when we're doing a read, this multiplexer here picks the result valid signal and forwards that as a ready signal to the decoder. And this is what causes the CPU to stall until the result of the LCD read becomes available. But since we now want to do out-of-order reads and have them behave the same as writes, we no longer need to distinguish between reading and writing, and the LCD unit can just use its busy signal to provide a readiness signal to the decoder. And we no longer need this multiplexer. Let's see how that affects our program. Let me reset the CPU and fast forward in the program a little bit. And when the program hits the first LCD read, the CPU is no longer stalled. Instead, it just kicks the read off to the LCD unit and then continues in the program. Let me step forward a few cycles. The LCD now reports that the result is ready, but the CPU is long gone and has run ahead in the program and continued executing other instructions. And so there's nothing in the CPU at the moment that would take this result that is now available and store it into the register file. So this result is just lost. And when I run the program to completion, we no longer get any useful results in the register file. The CPU has just stored a random value that was currently on the data bus whenever the LCD read was started, but then the read results never made their way into the register file. So let's give the LCD unit the ability to write to the register file. That will allow it to store its result independently from the CPU outside the instruction order. To get started, we need to decide who gets to write to the registers if both the CPU and the LCD want to write at the same time. I'm going to grab a fresh breadboard and then let's build a small arbiter. I'm going to add a blue bar graph LED here on the left so we have something to look at while we experiment with this arbiter. I'm going to connect one side to VDD through a resistor because most of the signals in the arbiter are probably going to be active low. So this will nicely invert those signals for us. And this arbiter is going to have a pretty simple job. There are going to be a couple of units, like the LCD unit up there and the decoder at the moment on the left, that may want access to the result bus to write something back to the register file. So all of these are going to have a request or a valid line that they will activate if they want access to the bus. And the arbiter should take all of those requests, pick one, set the ready signal, and give that access to the bus. And it turns out picking one of a bunch of request lines according to some priority is a pretty common problem to solve in hardware engineering. These are so common, in fact, that there are ready-made chips that implement this priority encoding logic. I'm going to use this 74HC148 chip, which is an 8-bit priority encoder. It has 8 active low input bits and a 3-bit output index, and it's going to look at all of the inputs and it's going to return the index of the highest priority input that is set. And I think the easiest thing to do is to just experiment with this a little bit. This chip has an active low enable input called EI. Let me tie that low so it's always enable. And then let me set all of the active low inputs to 1 so they are disabled for now. In addition to the 3 output bits, which basically indicate which of the 8 inputs has been selected, this chip also has a general select output, which indicates whether any of the inputs were selected at all. Let me hook that up to an LED. And when this chip is done picking the highest priority valid signals it takes as an input and produces its output index, we also want to then return a ready signal that's coming from the result bus back to whichever requester was selected. And so we're going to do this with the usual 74HC138 chip, which is a 3-to-8 demultiplexer. We've used this before in the decoder, where we use a similar chip to take the functional unit ID and turn it into a one-hot select line that goes to the different functional units. And it's basically the opposite of this priority encoder. The priority encoder goes from an 8-bit one hot signal or multiple hot signal to an index, and this demultiplexer will take that index and then fan it back out to an 8-bit one hot select signal. This chip has 2 active low and 1 active high enable signal. These we want to always enable. And then we'll take the 3 index bits coming out of the priority encoder and feed them into this demultiplexer. And then let me add 3 green LEDs such that we can look at the index that the priority encoder picked. Now the 148 chip is a bit weird because its output bits are inverted. And that's just a quirk of how this works internally. But it's worthwhile keeping in mind because the demultiplexer has its input bits not inverted, so the order of output bits is going to be reversed on that chip. I think that's all we need. Let's give this a test. Let me first connect the even LEDs on the bar graph to the priority encoder inputs 0, 1, 2, and 3. And then let me connect the odd LEDs to the corresponding ready return lines coming from the demultiplexer. And again, here I have to be careful to reverse the output order of the bits, because if input 0 is selected by the priority encoder, it's going to emit an inverted signal, so the index 7, and then the demultiplexer will activate its output 7. And the remaining 4 valid and ready return signals we just leave unconnected for now, but they will work exactly the same way. So let me power this up and let's give this a quick test. All right, currently all the input valid signals are disabled. So all of the even LEDs are off. No requests come into the Arbiter. And correspondingly, this LED that indicates whether any requests were seen by the Arbiter remains off. And the Arbiter will just pick the default input 0. And correspondingly, based on the 0, the demultiplexer will activate the ready return line at index 0. In theory, we could connect one of the enables of the demultiplexer to this general select output signal here, which indicates whether anything was selected, and have the demultiplexer not return a ready signal in case nothing requested anything. That would be definitely valid, but it's generally a good practice to keep the ready and valid handshakes as decoupled as possible, and whenever a ready is returned without a valid, the ready is just ignored. So it's not too bad to actually push this kind of distinction of getting a ready without having made a request, pushing that into the functional units to deal with this. And I think we'll do the same thing here. But now let's look at the arbitration. Let me set input 0. And as you can see, the valid 0 bit goes on because we're making a request on input 0. And the decoder indicates that there was at least one request line. It was at index 0. And then the demultiplexer still returns a ready signal to that requester. But now let's see what happens if I set a higher valid signal, for example, valid signal 3, the topmost one. Now the situation changes. You can see that the valid 0 input is still set, and now the valid 3 input is also set. And the priority encoder sees this, indicates that there was at least one valid input set, and it picks input number 3 in this case, because it is at the higher index. And the demultiplexer then sets the appropriate return ready signal, ready number 3, and ready number 0, which corresponds to the 0th valid, is not set. And in a similar fashion, if I set the valid signal at the lower index, for example, index number 1, the priority encoder is not going to change its selection. It sees index 0, index 1, and index 3 being set, and it picks the highest index, number 3, and outputs this here. And then the demultiplexer is still going to select that topmost one. And to finish off, let me deactivate the valid 3. And now the priority encoder picks index number 1, and the demultiplexer will then set the appropriate ready signal. So in this world of ready valid handshaking that we started to build out, we can present a bunch of valid signals to this arbiter coming from units that want access to the result bus, or in other words, that have valid data to write back into the registers. And then this arbiter will apply a fixed priority scheme to all of the inputs and set the ready return signal for one of them. And currently we get the ready all the time, but we can use the enable signals at the demultiplexer to, for example, have a ready coming from the register file in case we had one, and actually provide back pressure. So the arbiter would pick which input gets to access some resource like the registers, but then those registers or some other unit could still provide back pressure and set it's ready to 0, and the arbiter would appropriately forward this ready signal backwards to whichever request was picked. Pretty cool. Let's use this arbiter now to pick who gets to write to the register file. Currently, the write address is hardwired to the instruction bits 4, 5, 6, and 7, which is where the RD operand is. And the write enable and flags write enable are hard-coded to the RD mode and flags mode output from the decoder. Basically, the decoder is in full control of the register and flags write back because it has been the thing coordinating how data gets back into the register file. To allow other parts of the CPU to write back results, we need to decouple the write address, write enable, and flags write enable from the decoder and connect these signals to the result bus. And then whichever unit the arbiter picks can drive the write address, write enable, and flags write enable signals through a tri-state buffer. And we already do this for the write data. The ALU, the move unit, and the LCD unit have buffers that drive a result when they're selected. So let's go do the same for the metadata. We no longer need that bar graph LED on the arbiter that we used for experiments, so let's declare that bar graph LED the metadata bus, and basically the LEDs that show what's on the metadata bus. I'm also going to move the resistors of the bar graph LED. Currently it's connected to VDD to make the LEDs active low, but for the result metadata bus, we want them to be active high. So that gives us 8 metadata bits that we can populate with interesting additional information we need to write stuff back into the register file. The first piece of information is going to be knowing the write address, basically the register we're supposed to write back into. Currently, this is hardwired by the backplane behind this pipeline stack here. In fact, it's behind this program ROM. And when we designed this backplane PCB, we intentionally made this connection between the instruction bits and the write address easy to cut through. So let me remove the program ROM to gain access to that connection. This group of 4 jumpers, the second one from the right, is the one that connects the write address input of the register file to the instruction bits. So let me sever that connection. Let's make sure these things are now disconnected. That looks good. No more connection between instruction bits 4, 5, 6, and 7 and the write address input of the register file. Let's put the program ROM back, and then let's connect the lowest 4 bits of the metadata bus to the write address input of the register file. This will make metadata bits 0, 1, 2, and 3 correspond to the write address bits 0, 1, 2, and 3. For the write enable and the flags write enable, we need to be a bit more careful. If no unit requests the result bus, that is when this result valid signal here is off, nobody's going to drive the bits here on the bus, which means that the write enable and the flags write enable signals are going to be some random value that's just going to be floating. To avoid randomly writing to the registers or flags due to this undefined logic value on these signals, we need to deactivate the write enable and flags write enable whenever the result valid is off. Since these signals are active low, we can use a 74HC32 OR gate to only produce a write enable low when the write enable metadata is low and the result valid is low too. Let me grab metadata bit 4 and let's declare that to be the write enable. And then I'm going to OR that with the result valid coming from the priority arbiter. And then the output of this OR gate is going to be the write enable of the register file. So instead of taking the write enable from the decoder, we'll now take it from the result bus here. Then let me pick metadata bit 5 and declare that the flags write enable, and do the same thing there, feed this through an OR gate together with the result valid. And the output of that OR gate will now connect to the register file's flags write enable. So let me disconnect that from the decoder and connect it to the result bus instead. At this point, we have the result bus hooked up to the register file to drive its write data, write address, write enable, and flags write enable input signals. Since we have disconnected the decoder here from the register file signals, let's connect the decoder to the result bus instead, such that it can still drive the write address, write enable, and flags write enable signals for simple operations in the move and the ALU unit. I'm going to use a 74HC541 tri-state buffer chip, which we've used in a lot of other places. Right next to this multiplexer here seems as good a spot as any. This chip has 2 active flow output enables. Let me tie one of them low, such that that part is always enabled. The other output enable we'll need to figure out how to drive. For starters, let me tie that high. Let's connect the output of that buffer to the metadata of the result bus. And then let's hook up the input side. The lowest 4 bits contain the write address, so we want to connect that back up to instruction bits 4, 5, 6, and 7, the RD operand field. Then bit number 4 is the write enable. This we had connected to the RD mode 1 output of the decoder. And input bit number 5 is the flags write enable. This we had connected to the flags mode 1 bit of the decoder. This is starting to get pretty messy. I should do some cleanup at some point. So that gives us the old connections that we severed back, but this time through a buffer which we can explicitly turn on and off. Now we need to figure out when this buffer is supposed to drive metadata onto the result bus. So I think it's time to start connecting things to the arbiter. First, let's start with the move unit, which sits inside the register file. We want to make the move unit the lowest priority. Whenever any other unit has a result, it gets precedence and the move unit has to wait. The decoder uses this demultiplexer down here to turn the functional unit index into a one-hot select signal. So this is basically our valid signal that we send to the units. And index number 0 is the move unit. So let me connect that bit 0, the move valid signal, up to the arbiter's valid 0 input, which is the lowest priority. And then let me take the ready signal we get in response from the arbiter to the multiplexer the decoder uses to pick one of the ready signals coming from the functional units to stall the CPU. Up until now, that input of the multiplexer at the decoder has been tied to a constant 0, so basically always sending the ready signal, because there hasn't been any way for the move unit to stall the CPU. It was always ready to make progress. But now with the result bus in the CPU, any functional unit has to potentially give way to another functional unit and has to be able to stall the CPU. And then we also need to connect that ready signal to the move unit's output enable. So when the decoder wants to execute an instruction with the move unit, it requests result bus access through this white wire here with priority 0. And if the arbiter gives access using this green wire here, it enables the move output enable of the move unit. And if it doesn't do that, the CPU will stall. Then let's make the ALU the second lowest priority unit. I'm going to connect the functional unit 1 valid signal from the decoder to the arbiter's valid 1 input, which is the second lowest priority. And then we'll connect the ready signal we get in return again to this multiplexer, which decides whether we should stall the CPU or not. And again, that input has been tied low because the ALU was always ready and available to make progress, but that's no longer the case with the result bus. And then let's use that ready signal to enable the ALU's result and flags output whenever the arbiter picks the ALU with this ready signal. And as you can see, we're rapidly losing connections from the issuing side of the decoder, which picks which functional unit to execute an instruction on, and the actual control signals of those functional units to place the results on the bus. Instead, we funnel everything through the result bus arbiter, and only when the arbiter gives us access to the result bus do we actually go and enable those functional units. As a general strategy, we want to give units that take long to produce results a higher priority, since those results are expensive in a sense, and we want to let the units work on the next instruction. Move and ALU results are pretty cheap because they take a single cycle to compute, so these units get very low priority. And the last thing to do now is to decide when this metadata buffer gets to drive its data onto the result metadata bus. In a nutshell, we want to enable this whenever the ALU, the move unit, or the branch unit is selected, although the branch unit doesn't produce any results, so it's not that important. And conveniently, this multiplexer over here that we use to decide when to stall the CPU, it has a spare 4-input multiplexer that we can use for this. Its select input is already connected to the functional unit ID, so we can just use its output to enable that metadata buffer, and then we can hook up the 4 inputs. Input 2, we can connect to a 1 because the branch unit never writes, so the buffer doesn't need to be enabled, and input 3, we can connect to a 1 because the LCD unit will do its own write back, so this buffer also is not needed. Which leaves input 0, which corresponds to the move unit, which will want to connect to the ready signal coming back from the arbiter, such that when the arbiter actually picks the move unit to do some work, we can enable this metadata buffer and drive the metadata side of the result onto the bus. And input 1, corresponding to the ALU unit, we want to connect to the ready signal coming back from the arbiter for the ALU unit. So whenever we request the move or the ALU unit from the arbiter and that unit gets given access to the result bus, we'll also enable this metadata buffer here at the decoder to push the destination address and the write enable for the flags and the regular register onto the metadata bus. Let's test whether moves and ALU ops work via this new result bus connection. Let me reset the CPU. And then right at the beginning, we have a load immediate instruction, which loads an immediate value into register R0. The decoder selects functional unit 0, which is the move unit, and it sets the appropriate valid input signal over here at the arbiter for the result bus. And the arbiter, the priority encoder on the arbiter, indicates that at least one valid signal was set in its input, and indeed it picked the input number 0, lowest priority input corresponding to the move unit, to get access to the result bus. And it then sets this ready line here that goes back to this multiplexer over here, and then from this we set the output enable of the move unit, and correspondingly can see all the way over here the move output enable LED is on. And not only that, because it's a simple instruction, just a move, this metadata buffer here is enabled, and it drives the basic metadata that is necessary to do the write-back onto the metadata part of the result bus. And more specifically, the lowest 4 bits indicate a register address 1, which is R0, and the 4th bit is a 0, which means we're writing that register, and the 5th bit is a 1, which indicates that we're not writing the flags. And correspondingly, you can see that register R0 is selected for writing. The write enable lights up on that register, but for the flags, the write is not enabled. Immediately following is an LCD write instruction, and this time the arbiter here indicates that there were no requests to gain access to the result bus. The result valid LED here stays off. And indeed, that makes sense. For one, it's an LCD write, so we don't expect it to write anything back into the register file, but also it's the LCD unit, which will take a few cycles to ever want to write something back to the register file. And then immediately after this, we have another load immediate instruction, this time targeting register R1. And again, we're selecting functional unit 0. The arbiter indicates that there was a request for the bus and it came from unit 0, and it grants access to the bus, and correspondingly the move output enable is turned on. And then a few instructions further down the program, we have a flags write operation, and this one uses the ALU. And correspondingly, the decoder now picks the ALU, which is functional unit 1, to perform this operation. And it sets the input number 1 of the result bus arbiter here, and the arbiter indicates that there was a request, but this time it's input number 1, and it grants access to that unit, so correspondingly we route that ready signal back into this multiplexer here, and then also into the ALU. As you can see, the green LEDs up here indicate that we're writing onto the flags and the result bus. Let's see what happens if we had a higher priority unit want access to the result bus. Let me manually set the higher request line. Let me set input number 4, and when I do this, you can see that the arbiter now picks input 4 to get access to the result bus. And correspondingly, because the decoder is trying to do an ALU operation, and it sets the ALU request line, the ALU valid line here at the arbiter, but the resulting ALU ready line coming back is not set because another unit is requesting access and got access to the bus, you can see that the stall LED now turns on, because the multiplexer here checks whether the ALU ready return line from the arbiter is set. And this is not the case because we had to yield to another unit, so the CPU is now stalled. And this other unit that requested access and that was granted access has its ready signal activated, so that unit would now presumably drive the write data bus and also the flags write data bus, in addition to these metadata bits here. And that would allow it to write back into the register file. And the decoder would just patiently stall and wait until that access has gone through. And once that request is cleared, it's now the ALU that gets access to the result bus, and correspondingly the stall condition clears here, and we would make progress in the program now. And when I run the program to completion, you can see we get the same result as before. We don't get really any data from the LCD reads. So the result bus seems to work, and we can stall the CPU and prevent moves or ALU ops from executing if we request the result bus access with a higher priority unit. Let's add such a higher priority unit. The LCD unit is up here, and it's already in the right shape more or less to be hooked up to the result bus. It just needs a few minor tweaks. The unit currently has this green result valid LED here, which is nice. We can hook that up to the arbiter for the result bus, but the arbiter may decide to not give us access to the bus, so it makes sense to accept the ready signal we get back from it up here and do something with it. So as a first step, let me add a yellow LED, which is going to light up when we have a result valid, but we don't get a result ready back. Basically an indication that we need to stall. I'll hook up the result ready to this leftmost pin of the NAND gate. You'll see in a second why. But this now gives us a nice yellow stall LED on the result handshake. Now this result ready poses an additional challenge. We want to stall the LCD unit when we present a result valid, but we don't get a result ready back from the result bus arbiter. And in fact, the counter we've been using as the main driver of the LCD unit has this unused ENP input. This is a plain old enable input, which we've currently tied high such that it's always enabled. But we can use that to stall the LCD unit. And to get an enable, we can just invert that stall logic. We want to enable the counter when the result is not valid or when the result is ready. Let me connect the active low result valid to one input of the OR gate. And the other side, we want to connect to an active high version of the result ready. The result ready is active low at the moment, so let's use one of the NAND gates to invert that. We've already connected the result ready to one of the NAND inputs, and let me just connect it to the other one as well to turn the NAND gate into an inverter. And then let's feed that active high result ready into the other input of the OR gate. And the output of this OR gate is now an additional enable signal for our counter, which is the same as saying it's an active low stall signal. Let's quickly see if this works. I'm going to fast forward to when the first LCD read instruction in the program has a result valid. So right now the LCD unit is in the last cycle of its read, and you can see that the result valid LED is turned on. But since I've deactivated the result ready, the stall LED also turns on. And if I toggle the clock, the LCD unit just stays exactly where it is, and it's basically stalling and waiting for that result ready to be active as well. Let me pull that result ready low to activate it, and when I toggle the clock now, you can see that the LCD unit finishes its operation. Now let's make the LCD unit drive its result onto the right data bus whenever it gets a result ready signal back from the result bus arbiter. Let me disconnect the output enable of that buffer chip from the valid signal on the input side. And then in addition to driving the actual result onto the bus, we also need to drive this metadata onto the bus. And to do so, the LCD unit needs to remember which register it's supposed to write to. We already have this metadata latch here that we use to remember the RS and the RW setting for the communication with the LCD. And we can just use that to store the destination register too. I need a pretty long wire for this because the write address is pretty far away. So this basically stores the write address from the instruction bits whenever we start an LCD operation, and then we have it available when we need it. And as we keep building this out and make the CPU more sophisticated, a lot of these like random wires that fly around the breadboards here will turn into more cohesive issue buses and result buses and write back buses and execution buses that have a well-defined and kind of sensible set of signals that they carry around. But since we're building this out on the breadboard as an experiment, the signals go all over the place. So now that we remember the destination register, let's add a 74HC541 tri-state buffer, which is going to be the chip that drives all of this metadata onto the metadata part of the result bus. One of the output enables will connect to the result ready signal that we get back from the arbiter, and the other output enable will permanently tie a low such that it is always enabled. And then let's pick up the write address that is stored in the metadata latch and connect it to the lowest 4 bits of this buffer. Then bit number 4 of our metadata is the write enable. This we can permanently tie low because we always want to write whenever the LCD unit gains access to the result bus. And in a similar vein, the flags write enable, which is bit number 5 of the metadata, will permanently tie high because we never set the flags from the LCD unit. And then the output side of this buffer will connect to the metadata part of the result bus. Things are getting pretty crowded, which I think is a good sign. That means our CPU is getting more sophisticated. So that's both the write data and the metadata of the result bus hooked up to the LCD unit. And the only thing left to do is to hook up the result valid and result ready handshake signals to the arbiter of the result bus. Now let me pick input 7, which is the highest priority input, such that the LCD unit basically always gets to write when it needs to. And then we'll take the 7th ready signal coming back from the arbiter and hook that up to the result ready of the LCD unit. And I think that's all we need. Let's give this a final proper test. Let me reset the CPU and then fast forward a bit in the program. This is the first LCD read instruction in the program. It gets sent off to the LCD unit, which then stores the destination register in a latch together with some other bits indicating whether this is a read or a write and which of the 2 registers in the LCD we're accessing. And when I hit the clock, the LCD unit goes into its busy state and the CPU continues on in the program. So while the LCD is doing its thing, the CPU is going to do an add with immediate, a shift left, and an XOR with immediate. And 4 cycles later, the LCD unit has a result available and it sets the result valid signal here. At the same time, the CPU is executing an OR with immediate instruction. And so both the decoder here and the LCD unit request access to the result bus. And the arbiter takes these 2 requests and picks the highest priority one, which is index 7, the LCD unit. It then sets the result ready signal of the LCD unit, which you can see as the yellow stall LED not being on up here. So the LCD unit is requesting access to the result bus, and it is granted access to the result bus. It's a different story here at the decoder. The decoder is also requesting access to the result bus, for the ALU in this case, but since another unit has taken precedence, the ALU ready signal is not set. And the decoder notices that it doesn't get a ready response and stalls the CPU, which you can see by this yellow stall LED turning on. And correspondingly, the program counter is disabled, the enable LED has turned off. And because the ALU ready signal here wasn't set, the ALU's output enable for the flags and the result are also not set. So in a sense, this is the arbiter telling the decoder and the instruction front end of the CPU to give way to the LCD unit, which has higher priority, and so the instruction front end just stalls and waits for that to happen. And over here, the register file, you can see that the write data bus has the value 10 on it, which is actually the value we expect to read back from the LCD. And so we're not seeing the registers accessed by that OR instruction be enabled at the register file, but instead it's register R0 that is enabled for writing, which is the register that the LCD unit remembers it needs to store its result into. And when I toggle the clock, you can see the result of the LCD read, the number 10, appear in register R0. At this point, the LCD unit is no longer busy. It also no longer sets the result valid signal here because it was able to write that back. And now the arbiter is picking the ALU unit for access to the result bus. And so the decoder sees this and uninstalls the CPU. And now it is that OR with immediate instruction that gains access to the register file for writing. And indeed, it's register R1, the one targeted by that OR immediate, that is enabled for writing. And so when I toggle the clock, you can see that the register R1 is set to the value 15, which happens to be the result of that OR instruction. This is very, very cool. We do have a result bus now. The result bus arbiter picks between multiple units that may want to write results at the same time. So we have a proper arbitration scheme and the units can give way to each other. And we still have the decoder driving the move and ALU result right back, and it controls the stall of the CPU front end in case we want to do a move or an ALU operation and we don't get access to that result bus. And in the future, you can imagine that this will get even more decoupled. It will no longer be the decoder that orchestrates the write back of ALU and move results, but instead we'll have a completely separate part of the CPU dealing with the execution and then storing back of results into the register file. And the decoder is just going to be a front end to the CPU, which just gobbles up instructions from the program and it just throws them at different corners of the CPU. But the thing we have now is true out-of-order write-back of results. The CPU continues in the program even after an LCD read, and the result of the LCD read will become available sometime later when the LCD unit is done computing it. And as you've seen, the CPU is also becoming a lot more modular. We now have more of these handshakes. We have separate units making requests to the result bus and the units handling being stalled properly. And that is actually the foundation to making the CPU a lot more complicated. You don't want to have very complicated control logic that you have to keep in your mind all the time. Instead, you want to have these small independent units that communicate via very predictable and well-known interfaces, for example, through this ready valid handshaking, and they just orchestrate amongst each other, and the CPU then just happens to stall or happens to make progress depending on how the handshakes go. If I let the program finish though, you can see that there's a catch. We don't handle data hazards. If an instruction uses the result of an LCD read before it's available, it simply reads bogus data from the register file and then continues as if nothing happened. And if an instruction writes to the same register as an LCD read that's currently in flight, the LCD read will end up overriding that value once the read result becomes available. And our program actually checks this. Register R2 and R3 should be the value 10, and R4 and R5 should be the value 16, but they are not. Register R3 is the value 0, and registers R4 and R5 are the value 10. In the next episode, we will cook up a circuit that will prevent these data hazards and make the CPU stall whenever they occur. And then later, once we start to look into out-of-order issuing of instructions, we can find ways to start instructions that come later in the program that aren't held up by data hazards so that the CPU doesn't have to stall. That's something for the next episode though. I hope you've enjoyed this process of allowing the CPU to finish instructions in an order totally different from what is in the program. And we'll soon get to the other half, starting instructions in an order totally different from the program. Thanks a lot for watching, like and subscribe if you want to see more of this, and see you next time.